تمام. Okay, let us start it. You are welcome again in our class, organic class. So we want to continue our subject, but I will go back again to the chair conformation for the cyclohexane. Okay, so as we said before that, a planar cyclohexane ring experiences angle strain. That meaning we have angle strain here because the internal bond angle between the carbon atom will be 120. And I said to you before that any change in the angle for the tetrahedral figure 109.5 increase or decrease this value, it will be decrease the stability of the compound. So about the cyclohexane, if you look to the cyclohexane, I make this for you. Okay, this is the cyclohexane. Tamam? This is the angle here. This is the angle here is 120. Okay, this is more than 109.5. This make decreasing the stability for the cyclohexane. Okay, if you compare cyclohexane with مثلا hexane, with normal hexane. Okay, so any value more than or less than 109.5, it will be decrease the stability of the compound. So for example, if we have the cyclopropane, this is the cyclopropane, this angle here, it will be 60. So we have here very strict effect, very strict strain angle here, okay? Very strain angle here. And if we have, for example, cyclobutane like that, also this degree here, it will be 90, and also it will be decrease the stability of the cyclohexane. But any more is more stable, the cyclobutane or cyclopropane? Cyclobutane. Why? Because the value, the angle here, the value, angle value here is 90, okay? 90 is near from 109. But for the cyclopropane, this is the cyclopropane, the angle is so far from the real value is 109.5, okay? So, in cyclohexane, this is our subject now, this is the cyclohexane. And the tertiary strain, I said to you before that, this, if you have this cycloalkane, cyclohexane, we have here hydrogen bond, yes? For every carbon, how many hydrogen we have? 2 hydrogen bond. This 2 hydrogen bond, here 2 hydrogen bond, here 2 hydrogen bond. If the cyclohexane planar like that, planar, okay? All the hydrogen bond, it will be eclipsed to each other. Yani this hydrogen, it will be exactly with this hydrogen at the same side, okay? At the same side. And this 2 group, yani like that. If we have it, like that, okay? This, okay? If you look at it from here, this hydrogen to this hydrogen, they are eclipsed to each other, okay? This here makes steric effect and want to go to the more stable conformation, the Stiegert conformation. And this torsional also decrease the stability of the cyclohexane, okay? The torsional will be like that. It will be like that. This is the torsional strains, okay? So also we have 2 effects. We have the strain of the angle. Also we have the torsional effect. Do you understand? This is the torsional effect. So, if we go, he said here, so the cyclohexane adapt to Packard the conformation, okay? So the cyclohexane, it will be go to the more stable conformation, not as one planar, this one planar. It will be go to the chair form like that, okay? Chair form. This is the chair form. Chair form. It will be like chair, like that, okay? This is the chair form. So it will be go to the more stable conformation. Look, this the angle here is 120, yes? But if I make it like that, it will be 109.5. Okay? It will be 109.5, like the same value for the angle in the tetrahedral figure. Okay? So it will be go to the chair form. And this chair form can be changed to another chair form like that. It will be go to this another chair form. 1, 2. 1, 2. Okay, do you understand? Is it clear for you? Okay, this is the two chair form conformation for the cyclohexane. It will be changed at room temperature in normal condition. Okay, in normal condition. This is the chair form. So, in the chair form, I say to you, the angle here, it will be 109, like the angle value, like the value equal to the value in the tetrahedral figure. Also, the hydrogen bond here, this hydrogen and this hydrogen, it will be clipped, it will be staggered to each other, not eclipse. Okay, it will be staggered to each other. That meaning, and then the planar cyclohexane, all the hydrogen bond, they are eclipsed to each other. But in the chair form, the hydrogen bond, it will be staggered to each other. And you know, diamond, the staggered conformation is more stable than eclipse conformation. Why? Because less steric effect between the hydrogen atoms. Okay? So, what he said here, if we go here, for every carbon atom that has 2 hydrogen, one of them, it will be equatorial, as we said in the last lecture. One, it will be equatorial, and one, it will be axial. So, if we said, for example, this is the cyclohexane, chair form for the cyclohexane. Okay, where is the plane of the molecular planes? Where is it? Here, the plane of the molecules, like that. If we say this is the plane, the molecules must be like that, okay? So, you have, this is the plane, okay? This is the plane of the molecules. You have a 3 carbon down to the plane, this 1, 2, 3, okay? Down to the plane like that, down to the plane, and you have 1, 2, 3 up to the plane, okay? Up to the plane. So, it will be like that. This is the plane. So, the equatorial hydrogen, it will be with the plane of the... So, look, this now here, this is the hydrogen, it will be equatorial with the plane, look, with the plane of the molecules, okay? And this hydrogen, it will be axial hydrogen. For every carbon cyclohexane, one of them, it will be equatorial, and the other hydrogen, it will be what? It will be axial. Axial, that meaning is perpendicular to the plane of the molecules, okay? Like that, exactly like that. And the equatorial, it will be with the plane of the molecules. This about last lecture, and we stop here to the ring flipping and cyclohexane. Like a cyclic alkanes, cyclohexane doesn't remain in single conformation. Also, the fact, as we said before that, the chair conformation of the cyclohexane not remain in the fact and the real, okay, like that, just like that. No. We have conformation for the cyclohexane. As in the cycloalkane, in the aliphatic cycloalkane, okay, the open chain. As we said before that, for example, the ethane molecules. The ethane molecules can be found and staggered eclipse conformation, yes? We have a free rotation between carbon-carbon bond. So, also the cyclohexane can be found in many conformations like alkanes. And the bonds twist and bend, resulting in a new arrangement, but a movement is more restricted here, okay? It's in cyclohexane, the situation is more difficult than aliphatic alkanes, okay? One important conformation change involved ring flipping, which can be viewed as two-step process. Look, here, this is the first chair form here. Look, this is the first chair form. This carbon in the up and this carbon in the down, okay? One of them, not both of them. One of them, it will be changed to the up, okay? It will be flipped to the up. It will be give you boot form. This is the boot form. يعني شكل القارب, okay? The boot form. So, when this, it will be come to the up, you have two probability here. Or this go to the down and give you the second conformation, or this go again to the down and give you the same conformation. Do you understand? That meaning we have here two main conformation of the cyclohexane. One of them is the boat conformation, and the second is the chair form. So if you say to you, this is the first chair form. Okay, this is the first chair form, like that. Okay. Now this carbon in the down, it will go to the up. It will give you boat conformation. Okay. So if this go down again, it will give you the same conformation, the same chair conformation. But if this go down, give you the second conformation of the cyclohexane. Okay, give you the second chair form of the cyclohexane. That meaning this, it will be the flipping for the cyclohexane. Do you understand? It's so easy, but just like that. All this can be happened at room temperature. Okay, can be happened and room temperature. So again, so you have to be careful here. If you look to this three-dimensional figure for the cyclohexane, for example, we will go to take anyone, this carbon, okay, this or this carbon, this carbon. So all this, as I told you before, that every carbon here have two hydrogen. One of them is what? Is axial with the blue color, for example, and with white color it will be what? Equatorial. Look to this equatorial with the plane of the molecules. This the white hydrogen with the plane. This white hydrogen, white hydrogen, white hydrogen, white hydrogen. Okay, with the plane of the molecules. If you change this carbon to the up, the hydrogen also, it will be change the arrange the position of the hydrogen. So now for this example, if we go again to this, our example now here. Now, for example, this here, we have two hydrogen, yes? So slightly difficult like that. Okay, this is the equatorial, this is the down hydrogen, equatorial hydrogen, okay? Equatorial hydrogen. And to the up is axial hydrogen. So if I change like that, okay, the equatorial, it will be axial hydrogen, and the axial, it will be in the equatorial hydrogen. Okay, that meaning that also when you carbon atom flipped, the hydrogen also, it will be changed the position, and the axial hydrogen will be equatorial, and the equatorial hydrogen, it will be axial hydrogen. You have to be careful here. Look, like that exactly. When the carbon is to be flipped, also the hydrogen, it will be changed the position. Okay, it will be changed the position. And here, for example, this hydrogen, this is now equatorial, yes? But when you go to the flip, look, this come to here. This, it will be equatorial, and this, it will be axial. Okay, change the position. Change the position. Now, again, as I said to you, a down carbon flip up. Okay, down carbon, it will be flip up. This form a new conformation of the cyclohexane called boat conformation. The boat form has two carbons oriented above a plane containing the other four carbons. Okay, so this is the boat. Again, this is the boat conformation. Look, he talked about these two carbons. This carbon number 1 and this carbon number 2. Carbon number 1, carbon number 2. Look, both of them, they up to the other four carbon atoms. Okay, they are up to the 4 carbons atom. Okay, the boat form can flip in two possible ways. Okay, can be flipping, as I told you before that. And the original carbon labeled with the open sac can be flipped down. Okay, the other, it will be flipped down, reforming the initial conformation or the second up carbon labeled with what? With the solid cycle. Okay, as I show you here. Okay, as I show you here, this is the carbons here. We have here 2 carbons and we have 4 carbons here, and the flipping can be changed the position. The up, it will be down, and the down, it will be up. Okay, the down, it will be up. If the flipping happened for the 2 carbon, this, the chair form again. Now, we have 1 carbon to the up, 1 carbon to the down. This it will be go to the up, and this will be go to the down, give you the second conformation of the cyclohexane, the second chair form. Okay, go up, it will be go down. This is the flipping, okay? This, the flipping. Okay. Because of the ring flipping, the up carbon become down carbons, and the down carbons will be up carbons. It will be changed the position. The cyclohexane exists as 2 different chair conformation of equal stability. If I say to you, anyone is more stable conformation, the first chair conformation, this or this, this or this, anyone is more stable one. They are equal. They are equal in the stability. Okay, they are equal in the stability. There is no difference between this and this. Okay, why? Because now we talk about just cyclohexane. With all carbon has hydrogen atom, there is no substituent on the cycle. Okay, but if we have substituent on the cycle, the situation it will be different. Okay, now without unsubstituted cyclohexane. We talk now with unsubstituted cyclohexane. Okay, but if we go to talk about substitute cyclohexane, the situation will be different. So, axial and equatorial hydrogen atoms are interconverted during the ring flipping. Yes, this important. Okay, this important. When the flipping it will be happened, I said to you before that the equatorial hydrogen it will be axial hydrogen, and the axial it will be equatorial. Okay. So, the chair form of the cyclohexane are this 30 kilojoule per mole more stable than the boot form. Now, we talk about the stability. Okay. The boot conformation is destabilized by torsional strain because the hydrogen on the 4 carbons atoms in the plane are eclipsed to each other. Additionally, there are steric strain because the 2 hydrogen and the 2 up carbons, they are bonded to 2 up carbons, has steric effect, and this it will be decrease the stability. Okay. Now, here he said to you, this is the chair form and this is the boot form. Okay, the boot form, this is the boot form. Look to this 4 carbon, 1, this 2, 3, 4. Okay, 1, 2, 3, 4. All the hydrogen here, they are eclipsed to each other. Okay, all the hydrogen here, 1, 2, 3, 4, they are eclipsed to each other. Okay, they are eclipsed to each other, and this make torsional strain, as I told you before that. Yeah, and decrease the stability. And this is the 2 hydrogen here in the up. This 2 hydrogen. Okay. This is the 2 hydrogen in the up. Look, it will be like that. What we have here between this hydrogen and this hydrogen? What we have? They are near to each other or far to each other? Yes, they are near to each other. Also, this makes steric effect here, and this it will be make steric effect here and decrease the stability. That meaning we have 2 reasons for the why the boot, this is the boot conformation, is less stable than the chair form conformation. Why? Because here 2 reasons. The hydrogen here to the up, they has a steric effect. They are near to each other, and as I told you, the 4 carbons here, all the hydrogen bonded to the other 4 carbons here and here, they are eclipsed to each other. They are eclipsed to each other, and this make torsional strain like that, torsional strain. Okay, and the torsional strain also decrease the stability of the molecules. Understand? Do you understand? This here important note. You have to memorize this note, and why the boot form is less stable than chair form. Okay, you have 2 reasons. You have 2 reasons. So again, what he showed to us here. Look here. the boot form of the cyclohexane is less stable than chair form for the two reasons, as I told you. Eclipse interaction between the hydrogen torsional strain, because the hydrogen and the 4 carbon atoms, the down 4 carbon atoms, they are eclipsed to each other. And also the steric effect between the hydrogen bond, they are bonded to the upper carbon. Okay. Now this about cyclohexane and substituted cyclohexane, يعني cyclohexane without any substituent. If we have substituent on the cyclohexane, okay, if you have substituent on the cyclohexane, I told you before that the situation will be different. What happened when one hydrogen on cyclohexane is replaced by larger substituent? Okay, by larger substituent, by alkyl group. Okay, by alkyl group. There is difference in the stability between chair forms? There is difference between this chair form, the first chair form, and the second chair form? Okay, to answer this question, you have to memorize and remember one rule. دائما طلبة, the equatorial position. شو معنى equatorial position? Okay, what meaning equatorial position? يعني this, if I say to you this, the chair form, okay, where is the equatorial position? For example, here the equatorial position. Okay, this is the space here, not to the up, okay? The space here with the plane. If we say this is the plane of the molecule, this is the plane of the molecules, that meaning this is the space here, and this is the space here, okay? This is the equatorial position, okay? What he said in the equatorial position, has more room than the axial position. Room here come as meaning to the space, okay? J space, majal, okay? Not room, يعني room temperature, okay? To the room than the axial position. So larger substituent are more stable. Where is it? In any position, in the axial position, on the equatorial, دائما they are stable in the equatorial position. أو مهمة, okay? This is important note, okay? So in your exam, if I give you two مثلا conformation of the substituted cyclohexane, and I say to you anyone is more stable than other, look to the position of the substituent. Are the substituent, the position of the substituent equatorial or the axial? If the substituent equatorial, it will be give you more stable conformation than axial position, okay? أو مهمة. So, cyclohexane with one substituent. There are two possible chair conformation of mono substituted cyclohexane. Mono, what meaning mono substituted? Mono يعني with one substituent, okay? With one substituent. So such as methyl, okay, we will take methyl. Where is it? This is the methyl, okay? The methyl cyclohexane. So, draw the two conformation for the substituent of the cyclohexane. How we can draw the conformation of the cyclohexane, substituted cyclohexane. Step number 1, he said here, draw one chair form and add a substituent. Okay, this is the first chair form. This chair form. Okay. Arbitrarily picks a ring carbons, classify it as up and down carbon. Okay, you have to pick like this: 6 carbon, 3 of them they are up to the plane of symmetry, and another 3 carbon they are down to the plane of symmetry. And this is give you what? Give you the chair form. This is the chair form. This. Okay. Now this up and this up and this up to the plane. If we have the plane here, and this the other, it will be down to the plane of symmetry. Okay, to the plane of the molecules. So, and draw the bonds. Okay. Each carbon has one axial and one equatorial bonds. That meaning this carbon, this equatorial bonds, and this axial, this here equatorial, axials, like that, okay? This also equatorial axial, this also equatorial axial, this also equatorial axial, hydrogen, okay? For every bonds, for every carbon here, have one of them, it will be axial, and the second it will be equatorial with the plane of the symmetry, okay? with the plane of the symmetry. So, secondly, added a substituent. In this case, the hydrogen and CH3, you have put it. Where is the CH3, for example? If you want to put it here, equatorial. If you want to put it here and axial, okay? Just put it. For example, here they said CH3, here the CH3 and the hydrogen. And all other, they are hydrogen. All others atoms here. All of them, they are what? They are hydrogens, because we have just one substituent on the cyclohexane. So, this form one of the two possible chair conformation. This is the chair for conformation number 1. This is the chair for conformation number 1. Okay? Number 1. Secondly, ring a flip to the cyclohexane. Okay? Ring a flip of the cyclohexane. So, when the ring it will be flipping, I told you before that the up carbon it will be down, and the down carbon it will be to the up. Okay, it will be to the up, and this give you what? Give you this. They give you the second conformation of the cyclohexane. So, if this now, this carbon to the down, yes, this carbon now to the down. If I want to convert this carbon to the up, this equatorial will be what? Axial, and the axial will be what? Equatorial. Just remember this, okay? This is so important. When you draw the molecules, when you change the flipping, okay? Daim and daim, when you change the flip the carbons, the axial atoms, it will be equatorial, and the equatorial atoms, it will be axial. Go to the next slide. Okay? Look. The second conformation, this is the second conformation, okay? Draw axial and equatorial bond like that, equatorial bond, okay? And here, if you put the first chair form, the CH3, the alkyl group, at equatorial conformations, that meaning the second conformation, the equatorial must be chia, must be axial. Go to the axial. This, the axial CH3. Why? Because you make flipping. You make flipping. And this give you the second substituent. Draw axial and equatorial bond on down carbon and axial bond to the is down. Okay. Ring flipping convert axial bond to the equatorial bonds. هذا مهمة. Okay. أو مهمة. And reverse. Also it will be right. The equatorial methyl become axial. This is the equatorial methyl in the first chair form. This the equatorial methyl now. In the second chair, it will be what? It will be axial. Okay? This form the other possible chair conformation, labeled conformation as number 2. This it will be give you conformation number 2. Okay? Just like that. You have 3 steps. Step number 1, draw the first chair form and put the atoms, they are bonded to the carbon. Okay? For every carbon, we have one equatorial and one axial. Secondly, make a flipping. Thirdly, when you make flipping, the equatorial atoms, it will be what? Axials. And the axial will be what? Equatorial. And this gives you the second conformation of the substituted cyclohexane. Yani by easy way, this is the not so difficult. Okay? So, what he said, also the CH3 groups flip from the equatorial to the axial. It start on down bond and stay on the down bond. It's never flip from the below ring to the above ring. Okay. A substituent here always stay on the same side of the ring. A substituent, yani. Okay. If our substituent here, for example, here. Okay, for example, here. This hydrogen and this is the methyl. Yeah. This is the methyl, okay? This is the methyl here. If you make a flipping like that, okay? Substituent, now where's the substituent? And for you, it will be in the left side, yes? It will be in the left side. If you make a flipping, also it will be the same in the left side. But بالعكس, the equatorial now, axial. Equatorial, axial. But on the same side, okay? Don't make flipping like that. If your first molecule like that, make a flipping, and you have to convert this to here. No, no. It will be the same side, okay? Just a flipping. There is no like that rotation. Just a flipping. And he said here, as I told you, a substituent always, here, a substituent always stay on the same side of the ring. Okay? It will be at the same side on the ring. Either below or above to the plane. During what? During the process of the flipping. This is the flipping. We mean flipping just like that. Not rotation. Okay? Not rotation. Okay? Just a flipping. Just a flipping. Is it clear for you? Clear for you? So, as I told you before that, if I give you any question, I say to you, write the possible conformations of مثلا this molecules, or write the possible two-chair conformation of this compound. Any compound I give you, any cyclohexane with any substituents, okay? Just firstly, you have to draw the first chair form and arrange the atom, axials and equatorials. And then put your atoms, يعني بشكل عشوائي, put your atoms, okay? Without, if you want to put it مثلا in the first chair form, the CH3 or the alkali group in the equatorial or in the axial, as you want. But when you make a flipping, this is the important. When you make a flipping, okay, the equatorial will be what? Axial. And the axial will be equatorial. This is the important, not here. Okay. Do you understand the steps, how you can draw the cyclohexane? Now, the two conformation of methyl cyclohexane, this is the first chair form, and this the second chair form, okay? They are different. They are different. Where is it they are different? طبعا because the position of the CH3, okay? The CH3 here equatorial, and the CH3 here axial. So they are not equally stable. Okay, you cannot say this, the stability of this compound is equal to the stability of this compound. Not like unsubstituted cyclohexane. Unsubstituted cyclohexane, there is no difference between the first chair form and the second chair form. But here, no, we have different stability between the chairs form and the cyclohexane. So the conformation number one, this, the first one, is more stable. Look, 95%, okay, is more stable. Okay. Is more stable, which places the larger methyl group in the Romier equatorial position. Why? Because here, the CH3, where is it? As I told you before that, the important note, diamond, the more stable conformation, they put the alkyl, the substituted group, in the equatorial position. In the equatorial position. Why? Look, because here we have more space. More space. This more space here. Okay? More space here. Okay. This is more stable than the second conformation, and if you look to the second conformation, the methyl group in the axial position, the percentage of this conformation is what? Just 5%. Okay, that meaning the most conformation of the substituted cycloalkane, it will be in this chair form when the CH3 group or the alkyl group in the equatorial position. In the equatorial position. Okay? In the equatorial position. Now, again, why this conformation is more stable than this conformation? Again, the same reason here. The same reason here. This, look. Why associated cyclohexane in the ring more stable with, it will be if you compare the CH3 with larger atom here. If you make this CH3 group, not tertiary butyl, CH3 group, and the hydrogen here, if we go to the last slide, look, this is the hydrogen, 1, 2, 3. This is the methyl group, okay? Look here. This is the hydrogen, 1, 2, 3 hydrogen. This hydrogen, 1, 2, 3, they are near to these two hydrogens. Okay, and this what make here? Make steric effect. Okay, here make steric effect. This is the steric effect. because this hydrogen it will be near from this hydrogen. Okay, it will be steric effect. بينما when you have the methyl group in the equatorial position, look what we have here, free space. We have here free space, okay, more space here, and all the hydrogen, the methyl group, they are far from the hydrogen in the cycle, and this it will be more stable, the preferred one. Okay, it will be the more stable conformation here, chair form conformation. Is it clear for you, this and this? Clear for you? Okay. Now, why is substituted cyclohexane ring more stable with the larger group in the equatorial position? If we change, as I told you, not methyl, if we change it by bigger bulky tube, bulky group, bulky alkyl group, okay, what it will be happen? Are there flipping here? Can be the flip, it will be happened. Can be the two possible chair form, it will be founded here. Okay, if you change it with the alkyl group, with the big alkyl group. So the steric interaction, which nearly by groups, are minimized here. Okay, and the axial CH3 group, however, is close to the two other axial hydrogen, as I told you here. Here, look, he talked about here. About here. It will be they are near from each other here. So, grating to destabilize the steric interaction called 1,3 diaxial interaction. Okay, what is the meaning of 1,3 diaxial interaction? Do you know what meaning 1,3 diaxial interaction here? Oh, if we go here, okay, this carbon number 1, yes? Okay, what we have here? Yes, CH3 groups. And this 1, 2, 3. Look to the steric effect, not between carbon number 1 and 2. Yani with the hydrogen at carbon number 2. It will be carbon number 1 and carbon number 3. That meaning carbon number 1 and carbon number 3, we have here a steric effect. This is axial position, and this group also in the axial position. That meaning this the axial with this axial, it will be give you a steric factor here, steric effect here. Do you understand? This is the meaning of 1,3 diaxial interaction. Okay. Each infallible, the hydrogen and CH3 interaction between of them and destabilize the conformation of the chair form. طبعا by hand 3.8, this for example, kilojoule per mole. So the conformation number 2 is what? The energy, it will be 7.6 kilojoule. Anyone is more energy, this or this. طبعا this, the conformation is more energy and it will be less stable. More energy, that meaning it will be less stable. Okay? More energy, it will be less stable. Okay. Larger axial substituted declared unfavorable with 1,3 diaxial interaction. Okay. Destabilizing a cyclohexane conformation. Okay, it will be more destabilize the conformation if you have bulky group like that. Okay, bulky group like that. So the larger substituent on the 6-member ring is the higher of the percentage of the conformations containing the equatorial. Look, diamond, the bulky group, it will be in the equatorial position. In the equatorial position. In fact, a very large substituent, like مثلا this compound, tertiary butyl substituent, as a non-conformation containing axial tertiary butyl group is present. That meaning there is no two-chair conformation here. Just one chair conformation. It will be give you this, just this. This cannot be founded. This cannot be founded. Just this chair form, it will be founded. Any chair form, the alkyl, the bulky group at equatorial position. At equatorial, and there is no this chair form. Why? Because this is very stable. Very stable. Unstable chair form. Unstable conformation. Okay? So the ring is essentially anchored, okay, in angle conformation having the equatorial tertiary butyl group. Always we say diamond, the bulky group, it will be in the equatorial position. Diamond. أو مهمة. Okay? Look, this note is so important. All the times, the bulky group, it will be in the equatorial position. Now, this is clear for you? This is clear for you? Do you have a question? Do you have a question? Do you understand what meaning 1,3 diaxial interaction? Okay, the interaction will be happened between substituent on the carbon number 1 and carbon number 3 in the cyclohexane. Look here, this carbon number 1, this and this 1, 2, 3 here. The axial group here with the axial group here. We have interaction here. Look, it's so closer to each other here, so close to each other here. Okay, so we have here very crowded and high energy and destabilize this chair form here. Destabilize the chair form. Okay, do you have a question? So, if we go to the next slide here, homework, draw a second chair conformation. As I told you before that, such problems can be come to you here in your exam. Draw the second chair form for each cyclohexane. Okay, this cyclohexane, this cyclohexane, this cyclohexane. Then decide which conformation is present in higher concentration. Yani anyone is more stable. By another way, anyone is more stable. Anyone is more stable conformation. Okay, so this cyclohexane substituted the brom, and this cyclohexane substituted the chlor, and this with the ethyl. Look, ethyl group, and draw the second chair form this compound, and draw the second chair form this compound, also the second chair form this compound, and you have to decide anyone is more stable than other. Okay, about stability is easy. Diamond, the chair form with the equatorial substituted groups, it will be more stable than axial substituted groups. Okay, this for you. Diamond, always. Okay, the second homework here, when an ethyl group, this ethyl group, is bonded to the cyclohexane ring. Okay, 96% of the molecules possess an equatorial CH3CH2. Yani the more percentage conformation here, it will be with the equatorial substituted here, with the equatorial substituted group. Okay, when an ethyl group replaced by this, okay, by athenyl groups, okay, the percentage here, it will be changed. It will be to the 67% for the chair form with the equatorial position. Why this happened? Okay, explain. Why this happened? Explain. Okay, this is the idea from this question. So, I think it is clear for me, not for you. I don't know for you it is clear or not. Do you understand? Okay. Now, anyone is bigger groups, the ethyl or this group, the athenyl. Anyone is the bigger. Anyone is bigger than other. This group or this group. Look, both of them. How many carbon we have here? 2 carbon and 5 hydrogen. This 2 carbon, 1 hydrogen. That meaning anyone is bigger size. Oh, yes, the ethyl group. Of course, the ethyl group. Okay, the ethyl group. For this reason, the chair form for the ethyl group here, it will be founded. Okay, it will be founded by less percentage. Okay, so give reasons and this homework for you. Now, di-substituted cycloalkane. Now we finish from cyclohexane with monosubstituent. Okay, now what happened here if you have di-substituted cyclohexane? So just the idea here, as you know, okay, be careful, Abdurrahman. Okay, be patient. Come on. So if you have, for example, normal aliphatic hydrocarbons, okay, not cyclic like that, okay, that meaning we have a free rotation here, yes? free rotation here, as in ethane molecules, okay? So in ethane molecules, we have a free rotation between carbon and carbon. For example, this here, carbon and carbon, okay? Here we have a free rotation between these two carbons atom, okay? You know this. And this make conformations of the ethane, okay, of the ethanes, and eclipse and Steger conformation when the rotation it will be happened. And we have a free rotation without energy, free rotation here. So in the cyclic compound, for example, this cyclopropane here, between this carbon and this carbon and this carbon and this carbon, also this and this, we don't have rotation here. Okay, the rotation is restricted. No rotation here. Okay, no rotation. Also in, for example, the any cycle compound, this is the cycle, there is no rotation. Look, it will be restricted. Okay, rotation will be stopped. There is no rotation. Also on the cyclohexane, the rotation will be stopped. There is no rotation. Okay, so if we have, for example, these two groups here, okay, if you have this two groups here in cyclohexane, okay, this is the cyclohexane, okay. I will go, for example, to the cyclopropane, okay. This is the cyclopropane. If you have two groups here, this, for example, CH3, and this also CH3, okay. Now, the CH3 and CH3 in the same side or different side for this example? Okay, same side. Okay, to the up, both of them to the up. That meaning there is no rotation, the up group to go to the down group. Okay, now, both of them at the same side. Here we call it will be, is what, cis or trans? Cis conformation. This is the cis conformation, okay? So there is no rotation to convert the cis conformation to the trans conformation to this. There is no rotation, okay? This is the trans, look, this is the trans. Okay, this is the trans. This is the trans, the group in different side. This is the trans, okay, in different side. So, this is the idea. In the cyclic compound, there is no rotation between carbons of the cycle, okay? Of the cycle, there is no rotation. So, the upper group, if you have this, for example, the upper group, it will be remain upper, and the down, it will be remain down, okay? There is no rotation between the carbons of the cycle. Here, about the rotation, around carbon bond in the ring cyclohexane is what? Restricted. So the groups on one side of the ring and never rotate to the other side of the ring. Khalas. Cannot be changed the position of the group. This upper and rotation will be happen to go to the down. There is no this idea here. Okay, the upper it will be remain upper, and the down it will be remain down. So just I told you before that in the cyclohexane, the axial will be equatorial and the equatorial it will be axial, but it will be remain upper, down, down. Okay. So as a result, there are two different 1,2-dimethyl cyclopentanes, one having CH3 group at the same side, and the other it will be have both the group at different opposite side. One of them it will be called cis with the same sides groups, and with different sides groups it will be a trans. Okay, and here to the disubstitute alkane, I will stop today. Okay, I will stop today, and inshallah we have a time to continue us in the next lecture. So if you have a question, I can repeat for you. Do you have a question? Do you have a question? Do you have a question? No question? So just